Look at these two dashboards. On the left, a staging environment processing 10 requests per second, 0 errors. P99 latency is a snappy 12 milliseconds. On the right, production, on a Monday morning. The volume hits 10,000 requests per second. The error rate spikes to 12%. Latency balloons to over 3 seconds, and memory is climbing toward 2 gigabytes. The pull request passed every automated check. The QA team gave their approval. Yet the moment the code hit production, the incident channel opened, and the PagerDuty alerts fired. This crash happened because the service was tested at exactly 0.1% of its actual production traffic volume. Performance bugs that only manifest at scale remained invisible. At 10,000 requests per second, the service operates under a different set of physical constraints than it does at 10. As concurrency increases, the underlying behavior of the system changes. Connection pools saturate.
Garbage collection pauses stretch. Goroutine scheduling faces heavy contention. The code paths are the same, but the execution profile shifts as it hits the limits of the hardware. To build resilient systems, we have to deconstruct the 3 specific concurrency bottlenecks that break under high load, and then engineer an automated pipeline to catch them. Any staging environment that lacks production-scale load simulation functions as a demo environment. It cannot reliably predict how code will behave in a live production environment. The first constraint we hit at scale is connection pool exhaustion. Consider a database connection pool capped at 25 maximum open connections. If a query takes 5 milliseconds, a staging load of 10 requests per second requires only a fraction of a single connection. In practice, 10 connections process the slow trickle of data, while 15 of those slots sit idle. In this state, the configuration looks healthy. It utilizes a tiny fraction of available capacity, leaving the ceiling invisible to the developer. At a production volume of 10,000 requests per second, the math changes. Those 5-millisecond queries now require 50 concurrent connections. The pool instantly locks up at its 25 connection limit. Half of the incoming traffic cannot get a connection. 5,000 goroutines are forced into a sudden wait state every single second, piling up at the entrance of the pool. These waiting goroutines are not free. Each one must keep its execution stack and HTTP request context alive. As they wait, they consume hundreds of megabytes of RAM purely by existing in a blocked state. Meanwhile, the database CPU maxes out. The resulting strain slows query latency from 5 milliseconds to 15. The 25 connections are now held 3 times as long, which cuts the pool's effective capacity by 2/3. An oversubscribed connection pool creates a vicious feedback loop. A simple limit on the database side manifests as a massive memory and latency failure on the application side. The second failure pattern involves memory pressure triggered by unbounded goroutine allocation. A common pattern in Go is to spawn a background goroutine for every incoming request. This handles non-blocking work, like dispatching a notification, without slowing down the primary response. At 10 requests per second, this is invisible. Tasks finish quickly, leaving only a couple dozen active background operations. The memory footprint is negligible. This chart tracks active goroutines. If we take a production volume of 10,000 requests per second and combine it with a background task that takes 5 seconds to clear, the flat line violently spikes. We generate 50,000 concurrent active goroutines. Even with an optimized 16 kilobyte execution stack for each one, 50,000 parallel tasks demand 800 megabytes of RAM. If a minor latency spike in an external API causes the background work to take 30 seconds instead of 5, the multiplier expands. The system hits 300,000 goroutines, demanding 5 gigabytes of memory. This maxes out the hardware allocation and triggers an immediate out-of-memory pod kill. Background concurrency acts as a massive mathematical multiplier. A microscopic staging footprint can disguise a memory bomb that only detonates under production-level friction. The final failure point is mutex contention on shared state. Consider an in-memory cache protected by a read-write lock. Under normal conditions, reading from that shared map only holds the lock for a few microseconds. At 10 requests per second, the probability of 2 operations attempting to access the lock at the exact same microsecond is low. Contention profiles remain empty. When 10,000 concurrent readers hit that gateway, the timing overlaps. A single 50 microsecond write operation drops an exclusive lock, blocking all read access. This creates a lock convoy. In the fraction of a millisecond it takes to execute the write, Dozens of incoming read requests hit the barrier and queue up. When the write lock releases, the queued readers rush in simultaneously. That brief period of waiting is added to the total latency of every blocked request, pushing the 99th percentile response time into the red. Mutex contention is a function of load. It inflates request latency by milliseconds purely through microqueues, creating a bottleneck that is structurally invisible without massive concurrent volume. To catch these failures, we need to change how we run diagnostics. Many load testing tools rely on concurrent connections to generate traffic. If the target server starts slowing down, these tools lower their request rate to wait for responses. The top line here shows a concurrent connection tool. It adjusts its output as latency rises, hiding the true breaking point of the service. The bottom line shows a constant rate tool, like Vegeta. It maintains a precise attack volume regardless of how the server struggles. Constant rate generators form the core of the test, supported by tools like K6 for complex user workflows and GHC for gRPC traffic. However, high-volume traffic provides no diagnostic value if we don't capture the internal state of the server during the attack. We must measure 6 metrics simultaneously: P99 latency, CPU utilization, absolute memory, database wait statistics, active goroutine counts, and internal mutex contention profiles. Pairing a constant rate attack with real-time telemetry isolates the exact point where the system fails. Performance regressions often accumulate silently in weekly pull requests because load testing is treated as a manual quarterly event. The structural fix is to extract that constant rate protocol and embed it directly into the continuous integration pipeline as an automated performance gate. For every pull request, the CI system spins up a test container. It attacks it with a 60-second constant rate load, capturing metrics. The system evaluates the P99 latency against a rigid threshold, yielding a clear pass or fail verdict. If a slow query holds a lock too long, latency spikes, the threshold trips, and the pull request is forcefully blocked from merging. Comparative PR testing goes further by measuring the exact speed delta between the main branch and the new code. This catches the slow regressions that stay under absolute limits but degrade performance over time. This requires realistic data scale. Running 10,000 requests per second against an empty staging table will yield fast but completely useless results. The goal is a system that prevents code from reaching production if it cannot survive a simulated production load. Integrating load testing into the development lifecycle acts as the final guarantor that your code behaves in production as it did during development.